Okay, welcome to this lecture on mechanical vibrations, and we will going to continue with the topic that we were discussing last time. It was about base excitation, and we learned about the displacement transmissibility, and we went through the plot of the displacement transmissibility with respect to the frequency ratio, and we figured out some important points regarding that plot. So as I mentioned in the beginning of the previous lecture, that because of the base excitation, displacement and force both will be transmitted to the inertia element. And so in today's lecture, I intend to go through the topic of force transmissibility, and then in the end we're going to solve a problem on base excitation. So the equation of motion will still remain the same. For the case of base excitation, if you remember from the previous lecture, this was the equation of motion. And since this equation of motion is actually the summation of forces, we will say that the transmitted force is basically because of the, as you can see here, that because of the spring and damper forces. So these two components, spring and damper, together they are known as isolator, vibration isolator, as I mentioned. These components in the vibrating structure, that is the stiffness and the damper, these will be responsible to transmit the force to the inertia element from the base. If the base is moving, it is an excitation, and this transmitted force is actually equal to the inertia force. So we know that the particular response of the damped forced vibration is given by this expression x sine omega t minus phi, where x is the amplitude of the transmitted force now here. So if we differentiate this twice with respect to time, we will get this expression, and so we substitute this x double dot, the value of x double dot, in equation 1 here, and we get the value of the transmitted force, that is m capital X omega squared sine omega t minus phi. So this constant appearing here, that is the product of mass, maximum amplitude of the force, and the square of the excitation frequency, applied frequency, is the transmitted force, the magnitude of the transmitted force. So this means that the transmitted force, the dynamic force that is being transmitted to the inertia element because of the motion of the base or the support via the vibration isolators, that is the spring and damper, is actually given by this expression, the last expression on this screen. And here Ft is the magnitude of the transmitted force, and you can see uh, that the form of this expression, Ft sine omega t minus phi, it is exactly in phase with the response of the displacement, the amplitude of vibration of the inertia element. So the transmitted force remains in phase with the amplitude of the vibration. And since the amplitude of the force damped vibration is given by this expression, and this F naught for base excitation we proved in the previous lecture is given by this expression. So if we substitute these results in place of f naught here in this expression. Therefore, we substitute this f naught here in place in the expression for x, and then we have to put this x in this expression, the transmitted force. So therefore, this m omega square appears here in the expression of ft, and we say that the transmitted force in terms of k m omega and the base amplitude of base excitation is given by this expression. So we're going to try to make this non-dimensionless, as we have done in case of displacement transmissibility and the amplitude ratio. So we're going to take k common from the numerator and the denominator, and we're going to use these substitutions. mk equals to 1 upon m upon k equals to 1 upon omega n square, c omega k equals to 2 zeta r is omega upon omega n, and after this we will going to get the this ratio. Okay, if you will take this k common from this radical, k out from this radical, and you will be able to bring this ky in the denominator here in this expression, and we know that the spring stiffness multiplied by the displacement is the force. So this denominator is representing the input force that is being created by the vibration of the base or the base excitation, and this is the amount of force that is being transmitted. So this ratio is dimensionless, and it can be written in a dimensionless form like this. So in terms of only zeta and r. So again we see we are able to spot that this ft upon ky is known as the force transmissibility. Okay, previously we were able to get this kind of a ratio, and we say that this is the displacement transmissibility, and it was also a function of zeta and r. And here again we have obtained a dimensionless ratio, but this time this is known as the force transmissibility, and this is again in terms of zeta and r. So we can control the force transmissibility if we can control the value of zeta and r, the frequency ratio. So everything is same, only this r square has been added here, and since this is ft, so in the denominator we have a force that is k times y. Please note that this y is the displacement or the amplitude of the base excitation. If there is no base excitation given to you and you are not able to even calculate this, then this formula cannot be employed. So in order to find the transmitted force, the transmissibility of force, you need to know the stiffness of the system and the amplitude of the base excitation, that is the capital Y, because we know that in terms of base excitation, y as a function of time t, or the motion of the base as a function of time t, uh, can be written as this capital Y harmonic function. So you should be able to know this if you want to use this formula. Now again we can actually plot the values of ft upon ky as a function of zeta and r, and we can notice few important points. The first thing is that irrespective of all these values of zeta, okay, whatever these values are, 1, 0, zero point 0.1, any value less than 1 and greater than 0, you see irrespective of these values, all these curves approaches 0 if r approaches 0, or you can say that irrespective of the zeta, if r remains less than 1, then the force transmissibility irrespective of zeta will always remain less than 1. And this is good. You don't want uh, more forces to be transferred to your equipment. As you approach the value of r equals to 1, that is the resonance, you can see that there are some peaks observed, and these peaks are only for the underdamped cases. So for the critical system there is no peak, but you can also see that for critical system, as you increase r, the transmissibility of force always increases. It never goes down, it always increases for critical system. Okay, it is a very distinguishing result if you compare this with the uh, case of transmissibility of displacement or the magnification factor. For critical systems and overdam systems, those quantities were not important, because critical systems and overdam systems, they don't show any peak in that case. But here uh, this critical system is not showing any peak, but it is continuously increasing. Okay, so you can again say that for under dam systems this graph is important because it is showing some peaks, some maximum values. As you can see here, there is a peak here. If you further reduce this value of zeta, the peak value increases, and so on. Another important point is that if r is equal to under root 2, then irrespective of the values of zeta, all these curves tends to meet here at this point. But unfortunately this point represents the value of force transmissibility as twice. So whatever the force input is because of the base excitation, the force that is being transmitted is twice of that, and this is not a good result. If you go further beyond r equals to under root 2, you can notice that the graphs, it is not necessary that the the force transmissibility reduces, because you see for zeta equals to zero point 0.5 it is increasing continuously. For zeta 0.35 it is increasing, of increasing nature, and for zeta 0.2 zero point 0.1, okay, it first reduces but is still greater than 1, and then again it tends to increase. So in a nutshell you can say that increasing r in case of force transmissibility uh, will going to increase the transmitted force. Okay, however, if you notice in this graph, which is for the displacement transmissibility, you will see that if you go beyond r equals to under root 2 and even higher values, then for irrespective of the values of zeta or the damping present in the system, the displacement transmissibility will always be less than 1, which is a very good result. So looking at this figure, we can say that if we want to reduce the displacement transmissibility, we should increase the value of r. Okay, if material fatigue is not important, we should increase the value of r. But if we will going to do this, no doubt we will be able to reduce the displacement transmissibility to a value less than 1, but On the other hand, we will notice that the force transmissibility will be increased, and this means that more force is basically transmitting to your system. So basically, force transmissibility and displacement transmissibility uh, is basically a compromise. You have to make a compromise between both these things. And so, in terms of force transmissibility, it is, I mean, more meaningful to reduce the value of R as near to zero as possible, because in that case, you will going to have a transmission of force that is smaller than 1. Okay, and if you look at this graph as well, you will see that if you reduce the value of R, then you can reach the displacement transmissibility 1. Okay, almost 1 here. If you reduce the value of R and bring it closer to 0, the displacement transmissibility will also be 1 or near 1, if not less than 1. Okay, but the important factor will be the transmitted force. It will be less than 1. So it's a compromise actually. Okay, so we're going to move towards this problem. 3-55 of your textbook: an automobile is driven along a road whose elevation varies sinusoidally as shown in the figure. The distance from peak to trough is zero point 0.2 meter, and the distance along the road between the peaks is 35 meter. If the natural frequency of the automobile is 2 hertz, so the natural frequency is given to you, and the damping ratio of the shock absorber is 0.15. The value of zeta is also given. Find the amplitude of vibration of the automobile at a speed of 60 km per hour. When the velocity of the car is 60 km per hour, we have to find the amplitude of vibration. Also find the most unfavorable speed of the automobile for the passengers. So this figure, we can actually draw this figure by reading out this problem. Okay, they are saying that the road is basically an uneven road. It's a rough road whose elevation varies sinusoidally. So this is a variation of elevation sinusoidally plotted here, and they are saying that the distance between peak to trough is zero point 0.2 meter. Okay, so basically this distance is only 0.1 meter. Okay, this means that this distance is 0.1 meter. And this sinusoidal variation in the road profile represents the case of base excitation. So this can be considered as the base is sinusoidally moving, being excited, and your car is traveling with a speed of 60 km per hour on this road. It has some kind of a stiffness, some kind of a damping, because its natural frequency is given to be 2 hertz, and we can assume a mass of 1000 kilogram for this car. It's not given, but you can assume, and we're going to make use of this later on. So this, the distance between two peaks of this sinusoidal variation is 35 meters. Now we know that the amplitude, since this represents the case of base excitation, okay, and the base is being excited sinusoidally, so it is, we can assume this function yt as capital Y sine omega t, a sinusoidal function, and here capital Y is half of this value 0.2. So capital Y is zero point 0.1 meter. Therefore, we say that the amplitude of the base excitation in this problem is 0.1 meter. Now, if this is known, the y we have calculated from this figure and from the data given in this problem. So since yt was a sinusoidal function, that is y sine omega t. This y comes out to be half of zero point 0.2, which is 0.1 meters. And so this is now known to us, and we know that the displacement transmissibility x upon y is represented by this equation 1. And we need to find out this x. Okay, so zeta is known to us, that is 0.15. R is the frequency ratio, omega upon omega n. So we have to calculate omega, the frequency of this base excitation. That is this omega we have to calculate. Omega n is given to be 2 hertz. So R we need to calculate now. Now since the wavelength is 35 meters, that is the distance between the two peaks of this wave profile is 35 meter. Okay, frequency, velocity and wavelength can be represented with this formula, or you can say that the linear velocity v is equal to the product of the frequency times wavelength lambda. And we also know that this frequency in hertz can be written in terms of radian per second as omega upon 2 pi. So this means that we can find out omega from this expression. So omega is 2 pi v upon lambda, uh, and v is 60 kilometers per hour because the speed was 60 kilometer per hour. So we converted kilometers into meters and hour into seconds, and we get the frequency of excitation omega, that is 2.991 radian per second, approximately 3 radian per second. Also omega n can be calculated from the given natural frequency in hertz, that was 2 hertz. So omega n is 2 pi fn, and this gives us a value of 12.566 radian per second as the natural frequency of the automobile. And we know that this natural frequency can be written as under root k upon m. So we find out the value of r. It is 0.238, which is less than 1. So if this is 1, and this is the graph between the force transmissibility, sorry, the displacement transmissibility and r, and we see that r, the value of r has been calculated as 0.238. So it is less than 1, maybe somewhere here. And since this peak represents to zeta 0.2, this peak represents to zeta 0.1, and so slightly above this curve we will going to have our curve, and but that curve will also going to follow this trend and will reach somewhere here at at r equals to 0.238. So you see that r is already close to the value of 0, and in order to further reduce the displacement transmissibility to 1, because we can now substitute the value of r, zeta and y in equation number 1, and we can calculate the amplitude of uh, vibration of our inertia element of our car. Here in this case it was a car, and that comes out to be 0.1059 meters, which is 105.9 millimeters. uh, so it is slightly larger than the value that was used as an input, 0.1 meters. Okay, so the amplitude of base excitation was 0.1 meter, but what we are getting here is that the amplitude of the vibration of the car is greater than 0 0.1 meters. It is 0.1059 meters actually, so 105.9 millimeters. Now if we want to bring this closer to 1, closer to point to y, actually if we want to bring this x closer to y, that is this ratio approximately equal to 1, and which means that, okay, slightly greater than 1, and then 1 is better than slightly greater than 1 in terms of displacement transmissibility. So if you want to bring closer to 1, then this means that what we will do is that we will going to reduce r, we will going to reduce r more, we're going to move this point more towards 0, so that this actually reaches 1. Okay. On the other hand, if we increase the value of r, we can also see that by increasing the value of r, we can even reduce the displacement transmissibility below 1. In this region, you can notice, if we increase the value of r, the displacement transmissibility can be reduced uh, lower than 1. It can go low to a value lower than 1. But we have seen recently that if we increase the value of r, what will happen? The force transmissibility will increase. Okay, it can go uh, beyond 1. It might reach a value higher than 1. Okay, so increasing r is not feasible. Therefore, we have to further reduce r in order to reduce this transmissibility of displacement. The displacement transmissibility will be maximum. So you see that there are some peaks here, and at these peaks the displacement transmissibility is maximum, and when the displacement transmissibility reaches maximum, then it will be very inconvenient for the passengers. So the next part of the question was that find the most unfavorable speed of the automobile for the passengers. So if the passengers will going to feel more and more displacement, more and more displacement that is transmitted to the passengers, if they will start feeling this, then it will become very inconvenient for them, and this will going to happen when you are actually operating here near peaks. Okay, so the peaks uh, will going to occur at this value of r. Okay. If you can see this point here, the maximum value of displacement transmissibility, the maximum value of displacement transmissibility takes place at the value of r, which is given by this expression, 1 upon 2 zeta into under root 1 plus 8 zeta square minus 1 to the power half, and that is what we are using here. And by substituting value of zeta, that is 0.15, we get the new value of r, which is 0.979. So since r is omega upon omega n, we can calculate the new value of omega. That comes out to be 12.302. So you see that the new value of omega is 12.302, whereas the natural frequency of the car was 12.566. So it is very near to resonance. Therefore, maximum amplitude will going to occur. And by using this new value of omega, we know that the frequency, velocity, and wavelength can be related. So we get the new value of frequency 1.957, and from this we can find the new velocity of the car, which comes out to be 246.7 kilometer per hour. Now this value is a very large value, and it's very difficult to achieve this value. Even if you are driving a car with this speed, velocity 246.7 kilometer per hour, you are still not able to reach r equals to 1. This means that you are still not able to reach r equals to 1. So if you want to increase the value of r greater than under root 2, you have to drive faster than this value. So this is not feasible. Okay. So if you start driving your car with this velocity 246.7 kilometer per hour, you will going to have uh, maximum displacement, and that will be inconvenient. So that is why I told you that it is better to reduce the value of r and bring it more closer to zero, so that the displacement transmissibility remains approximately 1. Now when the base is excited, there will also be some dynamic force transmitted to the inertia element, as we have already seen here that there will be some dynamic force transmitted to the base, and this value is important for us. So we want to calculate this value, and this can be calculated from this expression of the force transmissibility. So we copy this formula here, and we say that ft can be calculated from this equation number 2. In this expression, everything is known to us. Zeta r is known to us, y is known to us, that is the amplitude of vibration of the base excitation. K is unknown, so we assume the mass of the car to be 1000 kilogram, and by using the formula of natural frequency we can estimate the value of K 157.904 kilonewton per meter, and by putting all the values in equation number 2 we will be able to find the value of transmitted force, that is 947.84 newton. Okay, so the force that is being input to the base is actually equal to the stiffness of the system multiplied by the amplitude of vibration of the base ky. Okay, and if you multiply zero point 0.1 by 157.904, you will going to obtain the uh, force that is being generated because of the motion of the base, but all that force is not being transmitted. Okay, because there was some damping involved, some stiffness was there, and 947.84 newton was transmitted. So this means that the ratio of ft upon ky is 0.06, so it is a very small value. And you can see here that this is the value of the force transmissibility because of the base excitation. On the vertical axis we have plotted this ratio, and so 0.06 maybe is somewhere here, because we know that r is less than 1 in this case, and that was 0.238. 0.238. So therefore you see that reducing r and bringing it closer to 0 is favorable in case of reducing the transmitted force as well. The transmitted force, the ratio of transmitted force is less than 1, 0.06. So we are basically below this one, and that is a good result, because if you increase r, okay, so I was telling you that it was better for us to reduce the value of r, because in this case we have actually reduced the force transmissibility less than 1. We are operating somewhere here where the value of r is 0.238, and not only we have reduced the value of force transmissibility, we have also reduced the value of displacement transmissibility. Okay, it is very close to 1. But on the other hand, if we increase the value of r, then you can see that the force transmissibility will again going to increase, will be increasing. Okay, if we further increase the value of r. so it will not be favorable for us to increase the value of R. So if you are driving on a rough road, you have to drive very slowly so that the value of R is as close as possible to zero. You are driving on a dead speed, and that is why the force transmissibility as well as the displacement transmissibility uh, will be approximately 1 less than 1. So this brings us to the end of this today's lecture, and we're going to meet again in the next lecture. Thank you.